This is Suse 13.1 with the Linrad installation where all the libraries are not yet installed. I will install iqplus here and calibrate it. So first we have to select how clever we are, and I press E for expert because I want some tools to show how the noise blanker works after calibration. Font scale, the smallest possible because this is a small screen. And we use these libraries, they are faster than the standard. And I specify the screen sizes as percentages. 99% by maybe 85. Process priority. I don't want any particular process priority, and Z for no auto start. And I type W here just in case, so this first primary setup will not be forgotten. Then I have to set up the input and output, and that is U. And for the iqplus I need a sound card. So I press A and sound card A. And I want to do the delta 44, that is 9. At 96 kilohertz, so I press 11. And this is 2 RF channels, so I need 4 audio channels, so that is 4. And the iqplus uses the SI570, that is 3. And now you got the message. It is not supported because I didn't install the libraries yet. So I have to do that before being able to use this software, but I configure the sound systems first. For the output, use the motherboard Intel sound system. Go to the main menu and don't forget to save what we did. At this point I have to exit, escape, and install the libusb or libusb 1.0. How to do that? Easiest is to type configure with help. And I have to look a little bit back here. We are on Suse, so this command will install what we need. Copy and paste. I could install the modern libusb as well, but this should work also. And after having installed the new library, it is necessary to run configure again. The configure script will change the header files, so Linrad will understand to compile with support for the SI570. So now I can run make x linrad and start Linrad again. And go to the submenu U, and here set the parameters for the sound card radio hardware. which is the SI570. I have to change the LO multiplier because it is 4, and for this hardware I need something else. As you can see, iqplus, it wants 2. Exit, exit, and save. Now I can enter the processing screen. That's D. Just accept default. And here Linrad is running, but there is no signal. We have to open the mixer program, Alsa mixer, and the sound card, select that is F6, and the M audio delta, and set some reasonable level, dB, let's say 5. Now all the 4 inputs have the same gain. We will need this later, and I make the signal fit in the window better. The frequency is 1.8 megahertz. We want 144, and here is a signal. It's a signal generator, an old analog thing. I can turn the frequency, as you see. Set some better, more suitable values here, and I don't need so much waterfall. The first step now in calibration is to calibrate the mirror image suppression. It is now about 40 dB from here to here, which is good, but we can improve on that. You can see the stability isn't so good. It's probably mostly the signal generator. I switched it on fairly recently. I will leave this running for a while before going into the calibration menu. This is the signal generator I'm using, and it's connected to the iqplus, which is sitting here, through a 3 dB hybrid. Before performing any calibration, one should start by setting the signal levels properly. I turn up the level on the signal generator. Hope something saturates. If I make it closer to the center, like that, we can see there are overtones. This is the desired signal, the mirror, the second harmonic, third harmonic, fourth harmonic. This is about the highest level one can use. The generator reads -27. I put it at -30 dBm, and look at what levels we have. We have 3 or 4 dB margin, which means it's a good idea to go here and make the gain a little bit higher by 3 dB maybe, so it should be 8 dB gain. Like that. And then we have nearly no margin anymore, but the output amplifier of the iqplus is driven fairly high. It gives a little bit of harmonic distortion. This could be a reasonable setting for levels. So I leave it running like this to stabilize before going to the mirror image balancing. To go to the calibration menu, that's X and C, and first calibrate the IQ phase and amplitude, that's A. And we have to reduce the level a little bit, like that. And then I have to sweep the frequency in steps of 3 kHz, that's 96 divided by 32. Oops. This is much easier with a stepped generator. Then one can just set 3 kHz stepping. But I make it like this just to show that it is possible. Oops. There is a coarse control and a fine control for frequency. But that was all. Compute the new calibration and store it in RAM. That's U. And I can magnify. It doesn't look I have any big discontinuities. So press enter. And now you can see that the signal is here and the mirror image isn't here. So this was very good. Let's save this. Save. And exit, that's X. And back to the processing menu with B. Here we are. And it happens to be very good at this frequency. I have to sweep it around to see if there is some frequency which wasn't so good. Yes. About here. No. This is about worst case. We have the mirror. There is the desired signal. Here is the mirror frequency. But here is the second harmonic and the second harmonic, and they are stronger than the mirror frequency. I will be satisfied with this, but you can do it better if you wish, and it's easier with the stepped signal generator. Now I have replaced the signal generator with a pulse generator. This thing contains a 555 followed by a divide by 2 and 6 AC MOS buffers in parallel to get enough current, and that is driven through a capacitor and a resistor to ground to form pulses of about 10 nanosecond length. The Linrad screen looks like this, and I go for the filter calibration, X, C for calibrate, and B. And the pulse repetition frequency is about 90 Hz. As you can see, the pulses are very long. That is the noise floor, and here is something that comes after, and it extends all the way down about here. That means that the high pass filter that is after the mixer, and to prevent probably 50 Hz and such things to reach the sound card, that is filtering away a lot of signal in the center region of the spectrum. To go into the calibration, I press enter. And here Linrad is collecting the average power in magenta, and it's the Fourier transform in powers, and the green is the average of the second derivative of the phase of the Fourier transforms. I will wait a while many pulses are collected. Now there are over 8,000 pulses, and that is more than enough. Compute the new corrections in RAM, that is U. And I just accept the defaults here, Y. And as you can see, it looks very flat. So I'm happy. That means save, S, and X to exit. And back to the SSB screen, B. And I will rearrange the screen a little bit. And as you can see, it looks pretty flat to within less than 0.1 dB. To show how the blanker works, I need to enable the second FFT, and I need to have the S meter. So I do this rearrangement as a preparation. We don't want the adaptive polarization at this time. And I move that away also. And then to enable the second FFT, that's X and P for parameters, and enable it, 1. And I don't change anything else. So here is one more window, and I move it away. And I eliminate the blankers. And switch on the oscilloscope. This is the reason why I logged in as an expert in the beginning of this video. You can see here the noise floor, and the pulse goes into saturation. I reduce the gain, that is minus here 6 decibels each time. You can see gain is now 1.0, and I go down. Here is the pulse peak amplitude, up where the mouse is. The white track is power, the sum of the powers in the two channels. And to look at the shape of the pulse, 6 decibels, 12 decibels, 18 decibels. So you can see there is a structure about 18 decibels down on each side of the pulse. Enable the smart blanker here. And we were 18 dB, so I go on here. 24, 30, 36, 40, no 42. So 42 dB down is here about, and that is twice as high, so 36 to 40, something like that, is how much the pulses are suppressed by the smart blanker. Now you can see here some points are red. Those points are not routed through the blanker. They appear here instead. And you can see it is low frequencies, but also some very high frequencies. It is here. There are some red points. And they give something near the Nyquist frequency. It means every second point is high and every second point is low. Look at it in the S-meter window. Want it in decibels and maybe a little bit more in detail. And I don't want the peak, I just want the RMS, which is here. So we have two channels and the RMS level is now 32 dB. If I disable the blanker, that's here, and I don't want to adapt polarization, the level is 57 or so, but this is a low pulse repetition frequency. If you had power line noise, it is pulse trains with typically 8 pulses repeating at 100 Hz. That's 800 pulses per second. It's something like that. And I have to do... This is a typical situation for power line noise, 65 dB. Enable the blanker. And then we have 33 dB. Disconnect the pulse generator. And the noise floor is only maybe 2 dB improved. This is very efficient, and it's only the smart blanker. The smart blanker is a linear process. It subtracts a pulse with the appropriate shape, so it isn't sensitive to the presence of other signals in the passband. There is also the dumb blanker here, and you see I can cut holes, but that doesn't improve. That is because you can see here it's a phenomenon coming from the level being too low. It has to be much higher. Something like this. And I have to bring these two up as well. Now we have no longer this. You can read about this instability problem on my home page. It's rather complicated. I can try to bring down the threshold, and make some effect of the dumb blanker, but it's a very small effect and one has to cut away a fairly large percentage, so it's not a good idea. It's better to leave it just non-active. The threshold for the smart blanker is very uncritical. The pulses are very large, so we just have to be a little bit below the level for a pulse. Just like the soft rock, the iqplus has a rather high corner frequency for the high-pass filter that is inserted between the mixer and the sound card input. For that reason, the polynomial fitting to remove the center discontinuity doesn't work. On the other hand, it isn't very critical because these hardware have very flat response at the high frequency end. They are essentially wideband circuits. So they run well, as you can see here, with only performing the first step of the pulse calibration procedures.